Okay, so we're going to start now on page 13. We're going to start talking about this thing called sampling distributions. Okay, we're going to talk about sampling distributions, what that is. Well, you actually have done a sampling distribution of your p-hats. You already did do that distribution of the p-hats when you did M&Ms. But now we're talking about means. So if you have a quantity, when you guys just did a quantity of your times, you made a sampling distribution of your means, of the averages. Okay, so we're going to talk about what the central limit theorem is as well today. But let's first start with these pictures. Let's kind of just look at the pictures up at the top and scan the page. These are a progression, and by the bottom of the page, you see how this ends up here. Okay, so at first, what is the shape of this distribution up here in the top left? It's very skewed to the right. Okay, the stretch and the skew are the same, so this is definitely skewed to the right. So very skewed right. Now, we are going to call this the population. Okay, so let's walk through what's in here. This is filled with individual values. So maybe this is the length of time that people stay at their jobs. I don't know. So this is an individual. That is a person and how long that person stayed at their job. This is a person and how long that person stays at their job, and so on. So this population is filled with individual people's lengths of times that they stayed at their job or whatever that was. Okay, some people stay really, really long. My father-in-law, he stayed, his whole career at one particular job. All right, so I want to talk symbols here because I want to change this. This has a symbol that is an X bar. I want to change that because I am telling you this is the population. The symbol that represents the population is mu for averages. It was P for proportions, but this is mu for average of the population. Okay, average of the population. That would be fine. You could cross this out down here, and you could rewrite. In fact, I'm going to retype these up for next year and put a mu there. And so then how about standard deviation? For a sample, it should not be represented by the letter S. If it is for a population, it shouldn't be the letter S. Do you remember what symbols? Yes, it's a lowercase sigma. Good, it's the Greek letter. So this is the sigma. This is the standard deviation of the population. Okay. So we can see up here that they have computed it's about 2. Both of these are right at about 2. So the population averages 2, and so on. Okay, so let me talk to you about what all the rest of these are. This here says n is 2. This one says n is 4. This one says n is 9. What does that mean when they give you these different n numbers? Yes, those are sizes of samples. So these are no longer that is not one single person in there. This is an X bar because that is an average of 9 items and people's times averaged together and put right there. So this is another average of 9 times and put right there, an average of 9 times and put right there, and so on. Yes, each X bar, every time you have an X bar, that's a sample mean, okay, of size n, whatever size. Perfect, very good. So this is a sample of size 4. This is an average of 4 people's. In this one, yes. And then up here, these X bars, that's an average of 2 people. Perfect. Very good. That's an average of 2 people. And so then let's look down here. Look, we're getting bigger samples. This X bar is you took 100 people's times and you averaged it. 100 people's times and you averaged it, and so on. So these are all of these ones down here are called sampling distributions because, so these are sampling distributions as opposed to the population. Okay, so label all these ones down here sampling distributions. And why would I call these a sampling distributions instead of the population? Because they are made up of what? What are all of these shapes made up of? Samples. Right? Okay, sorry, maybe that was too simple of an answer that you didn't know it. Okay, so a sample of 25, a sample of 16. Okay, so those are sampling distributions because they're made up of samples, averages of samples. Okay, now, what do you notice is happening about the shape from the top left corner by the time you get down to the bottom right-hand corner? It gets more symmetric. It started skewed, and by the time you get to the bottom, it gets more symmetric and unimodal. It gets much more normal shaped, right? Okay. So that's the main thing. That's the big deal that we have to pay attention to. How big did this sample size need to be in order for this severe skew to get fixed? Okay, let's take a look. Did a sample of size 2, was it big enough to fix the skew? No. But is it better? Yes, and same thing. Let's look at the sample of size 9. Is that big enough to fix the skew? It's better. It's still slightly skewed to the right, and so on. Now, look down here at this sample of size 40. This textbook said samples of size 40 are large enough to fix and make it normally distributed. Our textbook says 30. So our textbook says to be large enough, you need to have samples of size 30 greater than or equal to 30. And if your sample is greater than or equal to 30, then you will go from a messed up population to a unimodal and symmetric or normally shaped sampling distribution. So let me say that again. Listen up. What we know is that if your sample is large enough, which for means is greater than or equal to 30, then your population could be screwed up and all messed up. It could be skewed. It could be all these different things. It doesn't matter. Once you make a sample, you'll get a sampling distribution that's normal. Okay? All right. So so over here on the side, we have this question. Look what happens to the shape of the graphs as the sample size increases. So we can see that as n is getting bigger, what did you guys tell me about the shape of this distributions? Good. The shapes get more normal. Okay, very good. And once we hit that magic number of 30, then mathematically we can start using all of our normal model computing. And we can use z-scores and we can do norm CDFs and all of that kind of stuff. So that makes it really good. Let's look down here at the very bottom and do some notation. Let's notate the following. I've already kind of told you these, so let's do this again. Mean of the population. What will that look like? What symbol? Good. Perfect. That's like a cursive U. That's a Greek letter, mu. It's a lowercase mu. Standard deviation of the population. Good. The Greek sigma. Okay, very good. The mean of a sample. An X bar. Very good. Now, I haven't told you this. The standard deviation of a sample, actually, it's not supposed to be S, and we're going to learn this. It's supposed to be do you remember how previously we did the sigma with the little p hat? Remember? This one's going to be the sigma with the little x bars. Okay? The sigma with the little x bars. So what you're going to find is happening by the end of this chapter, we're going to have to be able to read a problem and know if it's a proportion problem or a mean problem. See, right now I'm separating them up, and we're doing means. But later you'll have them mixed up. So we'll practice that once we get there. All right, so let's take a look at what we got going on next. Actually, I want to, before we go on to these middle pages, let's look at page, what's this, 17? Turn over to page 17. I've put in my notes for next year to make this page 14, but for now, we'll have to deal with it. So we've got this song called Central Limit Theorem, because this is the name of the theorem, the statistical idea that is telling us about the shape that you guys were just looking at. So let's read what this says. The central limit theorem is about the shape of those sampling distributions, those drop-down sampling distributions, and the population, the one up there in the top left corner, okay, the population. So the central limit theorem is about the shape of those sampling distributions, the ones that's about the x bars, and the population. And here's what it says. If n is large enough, that's your sample size. If n is large enough, it does not matter the shape of that population up there. See, we had one that was really skewed. If n is large enough, it doesn't matter the shape of the population, because guess what you can say about the sampling distribution? The sampling distribution will still be normal. Okay, let me show you this down here. Look. Here is the original population. What symbols are inside there? These are filled with what kind of pieces of data? Good. These are regular X's. The population is individual pieces of data. These are plain X's, individual pieces of data. Okay, individual pieces of data. Now look at this second line. It says n equals 2. What does that mean I'm going to be dropping down? X bars. And that X bar will be made up of what? An average of how many items? 2 items. So I'm going to randomly select 2 items and I'm going to drop it down, average it, and put it right there. Randomly select another 2 items, average it, and drop it down. Okay, and so on. Let's look at these. Look at this one that started out uniform. Look at how it looked when you dropped it down. Isn't that interesting? Look at this one that started off. What direction is this skewed? Skewed right. Look at this one that drops down. It's still skewed right, but it is better, but it is not fixed yet. Okay? And now this one's interesting. This one's a bimodal. Do you remember that vocabulary, bimodal? They say that this one drops like this, so it kind of went into one that was single skewed right. Okay? So, in other words, were this middle line, were these ones here in the middle line fixed yet? No, the triangle's not normal. It is unimodal. Okay, and symmetric, yeah, but it's not this normal shape, okay? So these ones here in the center are no bueno. You know what's interesting? Look at this one over here on the left. Okay, that's weird. Why is this one here? Why is this one here on the left okay? Why is that one good to go? Haha, good, perfect. That's exactly right. Because the population was already good to go, then anything that comes out of it is going to be good to go. It doesn't even have to be large enough. Large enough is not necessary if we were told that the original population was normal. Okay, good job. So then everything that came out of it became normal. It was these guys over here that did not start out good that we had to be careful with. Okay, now I want to show you this really cool app. Oh, yeah, I forgot. We'll go ahead and do the song. Yep, here we go. We'll sing the song. And then we'll do this other little activity.
Basically, when the n gets larger, it gets more normal.
Yes, when the n gets larger, it gets more normal. Yep, here we go. I'm going to show you this picture as we sing the song so I can talk about it as we sing the song. Okay? Oops, that's not what I meant to do. Let's fix this here. Okay, here we go. Very good. I'm going to show you this picture. All right. Okay, let's see. Hopefully that's good enough to see both of them. There we go. That's good enough. Okay, you guys ready? Here it is. Song and picture at the same time so I can point to it. Here it goes. Central limit whereas this one up top is the population. Okay, let's keep going there. Sorry. Okay. Madeira is about the shape of the sampling distribution and the population. If it is large enough, it doesn't matter. The shape of the population, the sampling distribution will be normal. Central limit theorem is about the shape of the sampling distribution and the parent population. Okay, so that one up at the top is your parent population. Okay? Now that one's something else. We'll get to that later. Okay. All right, so this is your parent population. Now, I got one more representation of this to help you understand. It is, let's see here. Okay? All right. So now let's see if you can kind of I can walk you through this one last time. So I've now shown you this twice already. Here comes the third way. So look at this top. This top one is the population. So this has little X's in it. So we can say this is the average length people stay at their job. And the mean is 16. So say 16 years is the average length people stay at a job. Okay? I'm going to take the biggest that this picture will go to is 25. The biggest this will go to. So it's not quite 30, but we're going to go with it being close enough. So we're going to go with it being close enough. Actually, I'm going to let this one here be a small sample. Samples of only size 2. And then this one down here be big sample of 25. Okay, so here we go. I'm going to do an animated. And I think, yeah, we're not going to do that one yet. We're just going to do samples of size 2. So watch this. Okay, watch what just happened. Did you see here it just dropped down 2 items from up above, and it averaged them, and it dropped down that average. Okay, I'm going to do it again. There's 2 items, it averaged them, and it dropped it down. 2 items, averaged it, dropped it down. 2 items, averaged it, dropped it down. Okay, so as I do this over and over and over again, what do you think is going to happen? What shape will end up down here in blue? Well, the population started off normal. So this is going to be normal down here. The blue will be normal, even though the sample size is only 2. Yes. You remember this? If the population is normal, even if the sample size is little, we'll still have a normal shape. Okay? All right, so let's watch. I'm going to speed this process up and watch what happened a whole bunch. There it is. Okay? So look at that. So it's still normal. Let's do this again. I'm going to do it with the bigger sizes because I want you to see what happens. Let me do this one again with sizes of 5. I'm going to do this one with sizes of 25. I'm going to do, let's see what happens. 1, 2, 3, 4, 5. Averaged it, drops it down. Now it's going to take 25 items. It's going to average it, and it's going to drop it down to this bottom picture. Okay? 25 randomly chosen items, and there it dropped it down. I'm going to do that one more time, and then I'm going to speed up the process. There's 5 items, dropped it down. Here comes 25 items. I'm going to average it and drop it down. There it is. Wow, look at that. Dang, that doesn't necessarily happen. You want to see if it's the same again? We'll try it one more time. Here comes 5 items. Average those 5 and drop it down. Wow, look at how nicely that's right in the middle. Let's see what this one is. I doubt it'll be the same again. I would be surprised.
No, it's going to be to the right.
Oh, just right there to the right. Okay, so let's speed this process up a whole bunch and look at what happens. Boom. Okay, so the shape of them is still that normal model. Now, I'm curious, what do you think about the center? This top one has a center, a mean of 16. Look at what the mean of this other one is. This center one, this top blue one, also has a center. Oh, sorry, I didn't mean to do that. It also has a center of 16. Guess where the average of the bottom one is? Yes, all three of these have a center of 16. Now, it's over here on the side. It's told to me over here on the side. They got the actual averages, okay? Because it's computer, I mean, I don't know if they're telling me. Okay, here's one other thing. Listen up. I am interested in what's different between those shapes. I'm interested in they are normally shaped, but what's different between them? They're what? Closer together? Aha, you mean like this, the top one is more spread out, and the center one is closer to the center, and then the bottom one is, what would you call that in like, what's changing? What's a statistical thing that's changing that's making it more spread out or less spread out? The variation, which is what's the thing we use to represent variation? Standard deviation. Good, good. So of these three items, which one has the largest standard deviation? The top one. This top one has a standard deviation that is the largest because it's most spread out. So then when I take samples of size 5, what happens to my standard deviation? It becomes smaller. Okay, and then what about the samples of size 25? What can you say about them? It's the smallest of all. Okay, so as n is getting bigger, we are getting less varied. And so that actually is another thing that we could say about our stuff, is that as n gets bigger, we've got smaller standard deviation. Let's go ahead and go back to page 14. Let's do some drawings. So now you guys are going to not just listen, because I see some of you guys are kind of getting all cozy and nodding off here. This isn't so interesting. So now let's have you start doing some drawings based on what we've learned. Oh, I forgot to show you something super cool. Watch this. I'm going to make this thing totally messed up. Okay, look at that parent population. Isn't that just totally messed up? So messed up. Now, watch here. I'm going to do some small samples, and then I'm going to do a big sample. Let me animate it. There's 2 items averaged. Here's 25 items averaged. Okay? You got the idea? That's going to drop down to the bottom. Okay? I'm going to do that 5 times. 5 more times. Look at what's happening. What can you say about the one that is samples of size 2? Is it getting normally distributed? Does this top blue one look normally distributed? Not really. That's the correct answer, because it's only samples of size 2. Samples of size 2 was not big enough to fix that wacky problem up in the population. But look down here at the bottom. Samples of size 25. Of course, samples of size 30 would be better. Isn't this one at the bottom getting better looking? Yeah. So let's do even more. Okay. Still, is the middle one looking good? No. Is the bottom one getting better and better still? Okay. So again, the central limit theorem says it does not matter the shape of this population. If n is large enough, which is this bottom one down here, the sampling distribution will be normal. Okay, so let me get you guys drawing, because I'm losing you. Here we go. Page 14. I drew the parent population in there. It is, what's the shape of it?
Skewed right.
Skewed right. So write yourself in there so you remember. It is skewed right. Okay? What do you think? This second picture is samples of size 4. Is that going to be good enough to fix a problem? It will help it. Will it fix it? No. So I'm going to draw something. I don't know exactly how it's going to look, but I know it's going to be less skewed, but it's not good enough yet. So I'm going to draw something that's less skewed, but still not good enough. Okay? Less skewed, but still not good enough. Okay? Let's look down here. This bottom sampling distribution is going to be samples of size 30. What do you have to say about that? It's going to be beautiful normal model. Because if n is large enough, It doesn't matter. The shape of the population, the sampling distribution will be normal. Which of these three pictures is the sampling distributions? The bottom two are sampling distributions because they're made up of samples. The top one is the population, the parent population. Very good. Oh, this is a good question here. Which of these do you have the right to compute probabilities on? Only the bottom one. Why only the bottom one? Because what's the shape of the bottom one? Because it's normal. We can do z-scores and we can do norm CDF and we know the function of it. Do we know how to calculate the area of this right here? If it's this weird curve that we don't have the equation of? No. Likewise, we can't do it here. These you cannot compute the probabilities. No computing on the top two. Yes, computing on this one because it's normal. Okay, next page. So here's this one. Let's see if we can kind of talk about here's a parent population. What would you say the shape of that parent population is? What's the shape of that top left population? It's not even bimodal. It's like multimodal. Multimodal. Now, if I was to draw what's inside here, what would I put? X's or X bars? Plain X's because this is population, individual items. Population, individual items. I'm going to drop down samples of size 4 and I'm going to draw what it looks like. I don't know actually for real, but I have a suspicion. Anybody want to tell me what they think it might look like? I don't think it's going to be one big one yet. I think it's going to kind of be, yes, I agree. I think it'll average those two on the left and the two on the right. I agree. Now, what symbols would go in there since it is samples of size 4? Good. These are X bars. Excellent. Of sample averages of 4 items. Good job. Now, how about the bottom one? These are samples of size 30. What is that going to be? So it's going to be perfect. And these are X bars also. Good deal. Okay, let's do this top one. Top right. What is the name of this shape here? Okay, by the way, let me write multimodal here just as a review. Sorry. What's it called when it is straight across right there? Uniform. Excellent. That is uniform because all of the values are the same. I don't know why this one turns into a triangle. I was just looking at what the other paper said, but according to the other paper, it looks like a triangle. I would have to do a computer simulation to understand it. But by the way, what symbols go in this top picture? What kind of symbols go in this top picture? Plain X's. Why? Because this is one individual, population. Good. It says uniform. Okay, and then sampling distribution. What symbols go in here? X bars, because that is an average of 4 items. Average of 4. Average of 4 items. Average of 4 items. Okay, now how about this one? Average of 30 items, which is large enough. So what does that mean? It's going to be beautiful. Normal model. I don't know. They've just done statistical theory. Well, yeah, 29 will work. It's just going to take a little longer to get normal. Okay? Yeah, I don't exactly. Yeah, so because of the shape it started out as. And I'm going to tell you honestly, this middle one, I don't expect you to have to be able to memorize what these look like. These ones here, you know, you don't have to have these items. You don't have to be an expert at knowing those shapes. Those, I just know that they're not normal yet. And then I know that this bottom one is normal. Okay? So don't stress about needing to know the middle. Hey, which of these distributions do you have the ability and the right to compute probabilities on? Only the bottom ones. Okay, and then we're running out of time, so we'll talk about what happens there. We'll talk about what's happening to the mean and standard deviation when we do that on Monday, okay? So we've just kind of started talking about our sampling distributions.